All right, so we're wrapping up evolutionary programming today and then starting multi-objective. So last time I mentioned that there's a bunch of different types of genetic algorithms that came up roughly around the same time, and evolutionary programming was sort of one of them. And so in evolutionary programming, or EP, the interest was how do you have computer programs write other programs in using evolutionary methods. So create a population of programs, select them for certain functions, and have them be fine-tuned over time. And so at that time, to get around the issues of, well, what would the genotype be for a computer program if it's code? Well, you can't just mutate code very easily or recombine code and hopefully get syntaxes and everything. And so they used more abstract structures as their fundamental as their sort of fundamental building blocks for the genotypes that they used in evolutionary programming. And they basically focused on finite state machines. So as you likely already know, every computer program can be broken down into a finite state machine. So programs themselves have state, which you might depict as little circles. These are states. I have a state A and a state B, and I can get from one state to another. So these are oftentimes clocked systems. So every tick of a clock, I can move from one state to another, or I can stay in that state, or it can be based on an input. And so I could be in state A, and if I receive a certain input, then I can go to state B. And if I'm in state B, if I receive a certain input, I can go back to state A. And those inputs can, at the instant you receive those inputs, you can produce an output. And in addition, or instead, when you're in a particular state, you can produce an output. And so basically these finite state machines, you could give them a string of input, and they will then produce a string of output. And that's computation. So you could give them a string of input, a string of numbers, and then in the output, it will give you the sum of all the numbers that have come before. You could write a program to do that. Rather than writing code, you sort of can model that using a finite state machine. And so what evolutionary programming did is they said, if you draw me any finite state machine, I can write you code for it. So if you give me, I can say my program needs to act like this finite state machine. And there, of course, can be other states, plenty of other states, and they've all got links in and out, and so on. So for any finite state machine, there's a pretty simple way to turn this into code. You can write, there are all sorts of design patterns that are meant for translating finite state machines into code. So if you can just evolve the state machine and say, this is the best state machine for this task, then you can hand it off to a human will write it up as code, and then you can actually run the thing. So so what they would challenge them is they'd say, well, we're going to give you strings of inputs. So you could imagine, for example, lists of numbers. And then for outputs, you could imagine running sums. And so for these strings of inputs, rather than comparing to a fitness function, then there was sort of a desired output. And based on the distance from this desired output, you could then say this is a good solution or a bad solution. So you can make the fitness of a state machine is a measure of the match of its output to desired output. And then so now that we have a fitness notion, all we can create, we have to have a way to create a random population of state machines. We have a way to, for any state machine, evaluate its fitness. And so from then, all we need to do is a way to mutate state machines and recombine state machines. And if we can do all of that, then we could do everything we have in the GA. Well, they said we're not going to worry about recombination. All we're really going to have to worry about is mutation. So it's kind of like question 2 in the mini project 1. So all we have to do is figure out how to create a random population of finite state machines. And then from that random population of finite state machines, the ones, we'll select ones based on fitness to make it into the breeders. And then from the breeders, then we'll select ones to mutate to be kind of the offspring. And so, so how do you mutate these state machines? Well, you basically can say, is mutate kind of work on the graph. So the idea here is that you could imagine that for each, if you have a parent, so I guess I could say, you know, how do we mutate finite state machines? And then we're saying, well, then we will not use recombination. And so for each parent, you can basically choose to do things like change an output symbol. So if I were to go back and look at this kind of example I drew here, you could say, well, this, whatever output I've put in state A, I'm going to switch that to some other output, some other random output, and that would be to mutate an output. I can change a state transition. So right now I've got a state transition going from A to B. Well, maybe I'll actually cut that and actually make it from A to this other state out here. I can change, I can delete a state. I can maybe get rid of state B and all of the things connecting to it. I can add a state and then create random connections in and out of it. So basically you can do mutation on the graphs that are formed from the finite state machines, generating new finite state machines, and then run those finite state machines with that string of input, look at the string of output that they produce, and then assign a new fitness to that finite state machine. And so with that, you can eventually generate finite state machines that are good approximations of the input-output relationship you want. And that's effectively making an evolutionary method that writes code. Now, there's a modern version of this. So, you know, modern example for robotics that a group came up with in Europe called Automode. And so if you were to Google for that, and they're not the only ones that come up with this sort of idea, but it's basically the exact same sort of idea, but instead of going all the way down to the state machine, they went down to sort of primitives, like, you know, if you imagine what are all the things that a robot could do? Well, a robot can drive straight at a particular speed. So like if I was going to this sort of, you know, say related Automode. And so you could imagine that a robot could do things like, it has certain primitives like drive straight at a particular speed for a particular time. And you could imagine another primitive might be to turn, like drive along an arc, or to maybe turn in place. So you can imagine turn in place. And again, you could just say at speed for time. And so you see each one of these modules has a parameter associated with it. And so in Automode, what they've done is then they've created these programming specifications for how the behaviors of these robots are supposed to act. And they evaluate whether these robots as a team end up doing some particular task. Like maybe the task is finding all of the chairs in a room and pushing them to one side. And so they then they generate a random set of behaviors using all these primitives that are linked together in much the same way as a finite state machine. So the idea here is still, the similarity is they're basically doing mutation and selection on graphs. And so regardless of either whether the graph is a finite state machine or the graph is something at a higher level of a higher level of organization, you end up with a, and I see there's a question in this chat, you end up with a similar sort of idea where you can come up with a random set of behaviors, input-output relationships, and you can then select the ones that are best performing for the task at hand, keep those around, mutate them a little bit, try variations on them, and so on and so forth. And that's a way to evolve programs as opposed to evolving solutions to optimization problems. And so this was sort of the basics of evolutionary programming. And then things kind of matured a bit with genetic programming, which is what I want to introduce next, where recombination is added back in. So there's a question online, isn't mutation going to be erratic and a slow process? It takes longer. A lot of failed mutations end up with a beneficial mutation. It seems like it's going to take a long time finding the best set of finite state machines. And it is, this isn't this. That's one of the reasons why the auto mode people went to this direction. Because if you evolve the finite state machine at the lowest level, there's so many degrees of freedom that it's going to be difficult to get a program that does anything of high complexity. That's why typically when these evolutionary programming examples were added to the literature, they focused on relatively simple problems like summing up numbers, things like that, because those were kind of well suited. But if you wanted to do something like I want to evolve Microsoft Excel on its own, this would take a very long time to be able to find Microsoft Excel in all of the finite state machines that are out there. And so that's one of the reasons why the robotics people sort of took the same idea about mutation selection on graphs, but instead of going all the way down to a finite state machine, they went to these higher level behavior primitives that really sort of better scoped the search to things that might be useful in a robotics context. So that's why they and they have like whatever 10 of these primitives that are all like things that are little tasks that a robot could do that when strung together are likely to form a useful program. So there are ways to kind of guide this. So any other questions about this basic idea of you take the genetic algorithm we already know and hopefully are starting to love, take out recombination, and then define a genotype in terms of a graph genotype, and then just learn how to mutate that new graph. Yeah.
So if your genotype is basically a graph, do you know of any other attempts basically to like other models of computation? So for example, like evolving machine automata or Turing machines, or just like a generic programming language?
Sure. So I think the question is, are there? Well, I mean, so a finite state machine is pretty rich and expressive. So if you can evolve state machines, then you can evolve a whole lot of things. But it's not practical. So as we'll see with genetic programming, there are other ways that we can evolve code that actually make use of graphs that maybe are a little bit more practical in finding these things. But there have been, a lot of people work in this space. So I haven't really mentioned it, but you could also look into the artificial life community. I'll say artificial life or a life, and some great examples that have well-supported examples out there, like the Avita system from Charles Ofria at Michigan State. And so these are attempts to use evolutionary programming ideas to do open-ended evolution. So in these cases, you sort of actually are evolving ecosystems of artificial agents that interact with each other and with their environment that are just trying to do the things that natural selection does, maximize their proliferation. And so if you look in the worlds that are created inside of VITA, you just start out with a diverse set of programs, and those programs have to figure out the programs that happen to copy themselves are the ones that stick around. And then of those programs that learn to copy themselves, the ones that copy themselves more efficiently stick around longer. And then of those programs that stick around that learn to copy themselves, then you get diverse strategies where some programs learn to infect other programs and have those programs create copies of them. And that's pretty cool because then you get tiny little programs that use the machinery of the bigger programs to copy themselves, so they can actually have a lot of individuals. So those are the evolution of viruses. And so, yeah, there's been a lot of interesting explorations about this, where you're just using this idea of populations to explore very complex spaces, sometimes to do intentional things like this input-output relationship, other times to do so-called open-ended evolution, where you're just trying to create diversity that does cool things.
So I guess I could ask a person the same question, which is like, do you know if people in the literature have tried building like say training machines directly, or do people typically stick to finite state machines that work?
Right. So you're saying that and this is something that might be beyond the what's known to me, but I'm sure there are people out there. I mean, for example, if you look, we'll talk about cellular automata at the end of the semester, but there is, in the cellular automata kind of community, there's a lot of discussion about which cellular automata rules are Turing complete. And so that's kind of an example where you could say, what is the computational expressiveness of something that, so that's like a rule that a person came up with, but you could, do the same sort of things like, what are the limits to this? You could probably characterize this, and what types of solutions. I mean, here we're not asking for it to come up with a programming language or something like that, but I think you probably could try that. You could say, if I want, but it'd be hard to figure out how to put the selective pressure in to say.
So otherwise, you have to choose like a more powerful solution.
Sure.
I was just about the trade-off between the power of the representation and how hard it is to actually build it.
Absolutely. So there's a question about the evolvability. So there have been a lot of studies. When you're using evolutionary computation, the next step is to sort of say, how do I set up a population so that it's likely to do cool things? And that's a question in so-called evolvability. And so is, say, the finite state representation the most kind of evolvable genotype? What we'll see with, when we get into genetic programming here in a second, is that we find that there are certain aspects of, there are sort of like non-coding things that you can do in the genotypes that make the genotypes somehow easy. It makes it easier for them to find things in their search. And so, yeah, absolutely. This is definitely a rabbit hole that you can go down into, is for evolutionary methods of programming and related, what's the best genotype structure for the most evolvability? That's certainly, it's sort of beyond the scope of where I want to go with the discussion, but it's definitely a thread that you can tug and get a lot out of it. There was a question over here.
If you can't find the required code, then what?
Well, so the question of what happens when this thing never finds the required code. I mean, it always finds, it's finding an approximation. It might find something that solves the problem, but it at least, it may not be the exact code. Like there might be conditions where it doesn't do exactly what you want it to do, but it may be a starting point. So what a lot of people will do with evolutionary programming is they'll say, I don't really know how to start with this algorithm. So I'll do this, and this will get 99% of my use cases. So if I throw a unit test at an evolutionary programming solution, then maybe 9 out of 10 are, are checked. Then I can say, well, what is it doing? And I might be able to figure out what's going wrong in that 10th one and then fix it. So there can be kind of a co-creation where you use this to kind of help you get started, and then you can then, fine tune, or you can actually seed the populations with your own code. And then you can make an optimization objective, which we'll get into here, where I want you to make sure it passes all the unit tests, but I want you to do it using less power. So you can have some proxy for the amount of energy used by the program. And so then you provide the function, and then it optimizes some other feature that you didn't care about. Okay, let me see if there's any other questions. I see the hand there. Okay, go ahead, question? Say that again, is which based on?
Is it correct that the second question is a mini project one based on evolutionary program?
No, well, so there's a question, is the second question in the mini project relate to evolutionary programming? I don't know if it wasn't my intent for it to be. If you feel that it connects to this somehow, then I don't want to say it isn't, but it wasn't, it was for the second question in the mini project, I really was just trying to say, let's super simplify the GA so that it basically is a population of random walkers that get pruned away as they kind of, stray too far and get replaced with mutated versions of walkers that didn't stray too far, and how well would that do? That was kind of all that I was sort of intending there. But I mean, there's probably connections because, again, evolutionary programming is taking the exact same sort of GA and just applying it to a genotype that isn't an encoding for a number. Okay. All right, so this is, evolutionary program is kind of where it started. The more modern way to do this is genetic programming. Sometimes called GP, very often called GenProg. And it's a similar idea, but it's a different way to think about encoding. So naturally, we might think about code as finite state machines, but when we actually think about code we might think about programs as finite state machines. When we actually think about code, we think, well, how do we parse code? Well, we often parse code in these parse trees or abstract syntax trees. And so for any sort of abstract syntax tree, you can break down code into a tree interpretation. So as an example, if I do this is probably review for a lot of you with a CS background, but if I take the expression 5 times 2, well, I can view that from a tree perspective that is rooted at times and then has as leaves 5 and 2. Or I could consider something a little bit more complicated, like while I is greater than 5, I might do I equals I minus 1, end. Some little while loop. Well, I can break that down into a tree with several levels. At the very root of the tree is while. And then that, you can say, well, what are some of the arguments for while? Well, I've got its condition on one side, and its condition has got the greater than, which has I and 5 as its leaves. And then on the other side of it, I've got the body of the while loop, which is an assignment statement. And what is being assigned? Well, I is being assigned, so that's one of its leaves. And what is I being assigned to? Well, that's an expression. And that expression has a minus as its root. I is one of its leaves, and 1 is one of its leaves. So if I take any sort of procedural code, I can break them into these tree structures, these abstract syntax trees. And I can, what I'm going to do with gen programming is use these tree structures as my genotypes. And what's fun about this is that there is a type for each one of these locations. And so I know that there are particular, I'm expecting this node to give me basically a true or a false. I'm expecting an assign statement at this node. I'm expecting a number to come out of this node. So there's certain types there, which basically allow me, kind of like how if I go to a different gene, I can say, what are the alleles for this gene? I can do the same sort of thing where I can say, I can put any subtree I want here, just so long as it shares the same root type. So this allows me to start with very simple programs and actually grow them into very large programs, just so long as there is agreement. If I want to mutate this node, I just need to replace it with something else that agrees at the level of this node. So everything else is kind of hidden. So any subtree that produces a number is going to be legal here. And what's cool about that is not only can I do mutation, but I can do crossover. So if I was able to look at, if I have two programs here, I basically, as long as if I can find two nodes that agree in kind of type, then I can cross them over. So for example, this whole section here, 5 times 2, I can actually put it in here for this and swap that one back out. So I now have a way that I can cut through these trees and then swap subtrees in exactly the same way. So I can define crossover on abstract syntax trees. I can define mutation on abstract syntax trees. So now I can use the standard genetic algorithm with crossover, with mutation, and I can use it to actually write code, not finite state machines. And that's kind of how GenProg works. And I don't know if I went into, let's see if I go into any more. I think, yeah, the detail here. Yeah, so as an example, so I mentioned, now I can define crossover on abstract syntax trees. So I basically can swap matching subtrees. And so an example here is I could have two programs, 2x, two expressions, 2x plus 3.14. And on the other side, I've got this program x times cosine of 4.5. Now note that 4.5 and 2x agree in kind, in type. So if I was to draw the abstract syntax tree out for both of these expressions, then there would be a root corresponding to 2x that I could swap for the subtree rooted at 4.5. I could just swap those two out together. So if I were to do crossover, then that could produce two offspring, which would be 4.5 plus 3.14. And on the other side, x cosine times 2x. It's there. Two programs can now have sex and produce two offspring that are mixtures of the two. That's how we implement crossover in genetic programming. And then mutation works the same way, and I see the question, and I'll get it in a second. Mutation works the same way as it did with the evolutionary programming case. So if I need to introduce a mutation, I can go to any particular subtree, and I can actually swap in a whole random subtree. I need a way to generate random subtrees that agree with that root node, but I can do that. So that's sort of saying I need for this subtree, I need this to be a Boolean. And so I can say, well, my options for that are a literal, true or false, or my options might be all of the relational operators, less than, greater than, etc. If I choose a less than, well, I can't just choose a less than alone. So I need to choose a random, a random operand for the less than. So I'm going to choose, X is an option, so I'll choose X, and Y is another option, so I'll choose Y. So then X less than Y becomes my random predicate that I'll end up putting in there. So you can mutate in the tree way like we were doing with the evolutionary programming, but we can also do crossover because we can swap things out and everything matches. And then so now we can just then use standard GA with mutation and crossover operators tailored to abstract syntax trees. And then, what's your fitness function? Well, this fitness function, I kind of mentioned this already. People now do things like, we're going to measure the energy use of this program. We're going to measure the memory footprint of this program. So you could create all sorts of fitnesses that are related to the operation of the program. How well does this program solve a particular problem? Does it generate, I'm going to have, how many test cases does it fail? I want to minimize that. So you can come up with all sorts of fitness functions that are relative, that measure the performance of your program. Is there a question in front of you?
My question was, how did you know that the 2x and the 4.5 would swap? Because to me, it seems like the 2x is like the best thing to swap with is the entire x cosine 4.5. Those are both like y essentially. But I don't know.
Well, so the question was, how do we know that we were to swap 2x and 4.5 and not 3.14 and 4.5 or something like that? And we don't know ahead of time. We let the GA do that for us, and we just allow for random crossovers. And so there, like if these were just numbers, we would have picked a crossover point between genes 2 and 3, and then genes 1 and 2 would get crossed over, and the rest would stay the same.
You said that they were alike, like optimal. So what do you mean by they're alike, and what would be a case where they're not alike?
Oh, gotcha. So the idea here is there's a bunch of different ways you can implement a crossover operator, but I mean, the basic idea here would be, I'm going to go to one of my parents, and I am going, this is kind of this example is a little silly because it's so small, but you can imagine this is a much bigger tree. But you could go to one of your parents and pick one of the nodes in the tree as a crossover point. And you could say, I want to cross over here, which basically means I want to take this subtree and I want to swap it with another parent. And then so then I can then go through this one, and then I can then find a matching spot where I can then swap those subtrees out. So because things aren't so linear, it's not so easy to say, I'm always going to swap. Like I'm going to draw, I know there's 15 different places I could swap. This time I'm going to swap at position 7. And then everything before 7 gets swapped and everything after 7 stays the same. Here, it's a little, again, less linear, but it's the same basic idea. Find a random subtree and then find a place that you can swap out that subtree and swap in another subtree. Yeah.
I was going to ask if the swapping can only be done with the leaf, but you just answered my question.
Yeah, right. It could be, it's generally going to take everything under it. But yeah, so if I would have, I should have maybe written an example where I had more stuff going on here. And then that way so you're not just swapping a leaf for a subtree, you can swap a whole subtree for another whole subtree. Any other questions? Let me check online to see if there's questions. So there's a question online. Did you swap 2x and 4.5 in order to get like terms on the same side? And that is effectively right, that I didn't have to pick 2x and 4.5. I could have picked 3.14 and 4.5. That would have been a fine crossover as well. But the point here is that if you were to draw out the abstract syntax tree for this whole thing and then pick a random node, imagine I picked the 2x node, which would be multiplication x2, and it would be the 2x. If I were to pick that thing there, then I now need to say, okay, I've got a subtree. I need a place to put it. Let me go over in my other abstract syntax tree and find a legal place to put an arithmetic operation like multiplication. And a legal place to put an arithmetic operator is a literal, is a numerical literal, because they both return numbers. So I can swap out this number and put it there, and I can swap out this operation and put it there, and I still get legal syntax. So the key here is it's crossover that produces legal syntax. And then let me hit another question online. So is this like solving two equations, getting values and putting them in the mutated equations? What would you mean by crossover in this case? And they said, okay, got it. Right, so we're not solving equations. We're actually thinking, I'm just writing these expressions here as examples for programs, for procedural programs. So it looks, they happen to all be math, but likewise, like in this example here, I've got an abstract syntax tree, which actually is a whole program. So this same experiment, although for simplicity, I wrote it as two mathematical expressions, this could have been a while loop, and this could have been a for loop, and they might have swapped their bodies here. So, and that would have been, or they would have swapped maybe the for out and the while out or something like that. So you can imagine more generally something that looks like this syntax tree. Other questions in here? I thought I saw, okay. All right, so that's GenProg. There are a bunch of other sort of offshoots of GenProg that have tried to implement crossover without using abstract syntax trees. They require limiting the type of program code that you're writing so that it's a little bit more flexible to just kind of random swapping in and out of things. And so there are, for example, other GenProg approaches. There are languages where you just have a linear string of instructions with how to sort of say this. So if we so the big problem with the generic code, like writing Java code or whatever like that, is that each line of code refers to variables that might have come before, that might have come after. It might refer to a structure on the in-between. There's a lot of structure that's spread out across across the lines. Now, if we have languages that depend upon a fixed set of registers in a computational architecture, then in that case, we often can just swap out parts of the code for other parts of the code, and things are still syntactically correct. So if we have languages where everything is atomic, so sort of every statement, every instruction stands alone, then we can actually perform mutation and crossover because we don't have to worry about swapping something in the right place. So as an example for this, you can look up, if you've not heard about this before, like a one instruction set computer. So that's one instruction set computer. And sort of the like most famous variety of this is subtract and branch if negative. And so basically there are architectures out there that do something like a single instruction. So this one, subtract and branch if negative. This, what you're saying, what are you subtracting and what do you mean branching? What this is saying is there are a set of registers, sort of memory locations, that are always assumed to be there. And these instructions can refer to those register locations to say, well, take whatever's in register A and subtract it from whatever's in register B, and and then store that in register C. And if that is negative, or in this case, it's all one register, but if that result is negative, then branch to the program counter location that's stored in register D. And so you can actually write every single program that you can write in C, you can write with a one instruction set computer. It can do everything, but you don't have these lingering code blocks that need to be held together. And as a consequence, it's easy to mutate each line. It's easy to swap lines in from one bit of code to another bit of code. And you don't have to worry about maintaining syntax across lines. So this is one way that people have also played with genetic programming, is to just create sequences, create sort of coding languages, or make use of coding languages that are a little bit more kind of DNA-like, where you can just kind of take a chunk, pull it out, and then put in another arbitrary chunk. And it doesn't really matter, like the machine's not going to break, it'll still execute. Whereas, if you take a chunk of C code out and put an arbitrary other chunk of C code out, you may not even be able to compile again, but these will always work. So that's the other kind of approach that people have taken. Now, what's kind of interesting about these is when they do things in this way, then they find that, like, again, so there's branching statements that happen here. So very often you get programs where there's only really 4 or 5 lines that are actually being used. And there's a bunch of lines in between that are just getting jumped over. And so these are sort of like non-coding regions in DNA. And when programs have these long non-coding regions where you've got a bunch of instructions that are basically just noise, but it's not ever pruned out because there was no pressure to get rid of them because they weren't being executed, they're just being jumped over, then you end up actually getting more evolvability. And what I mean by that is you can get these sort of jumps in function. And what's sort of is happening is, like, what you'll end up getting is a bunch of individuals that maintain their base function with these like 5 lines they're actually using. And with the 25 lines they're not using, those are getting mutated in ways that are not screwing up the function of those base functions. So those individuals never get swept out of the population because they're perfectly fit. But they're writing sort of refactored, better code in the lines that aren't being used. And then one mutation later turns those codes on. And then suddenly a new functionality emerges, and these end up becoming even better programs. And so you've kind of like, if you've got 10 test cases in your unit test, you might have individuals that are only solve 5 of them. But then some of those individuals have non-coding regions that aren't even getting executed, but they're mutating. And what you don't realize is they're actually starting to get closer to solving the 5 test cases that you haven't been able to solve. And then suddenly they get turned on, and you can suddenly solve a large fraction of those 5, and then they sweep out all the other ones. And so there's a question earlier about, like, richness and what sort of languages are best for this. And this is one of the things that sometimes these architectures maybe have an improvement over the kind of abstract syntax trees, because there's kind of more opportunity for junk to accumulate, junk that can kind of evolve in the background and not hurt anything. And then it gives them kind of more time so that you don't have to solve a new problem in 1 generation. It allows you to solve it in 20 generations. And then you get to sort of turn it on and see, after 20 mutations, what's happened. And so that's kind of one of the reasons why people investigate these approaches as well, even though the abstract syntax tree is sometimes a little more elegant looking. Questions? Question?
Okay, so first of all, I've actually seen like non-coding regions can show up also in abstract.
Sure, they absolutely can. Yeah.
The question then is, so we have, say, like registers and type guarantees.
Mm-hmm.
A lot of the time, right, there's like when we make mutations, we know that the mutated code basically will be error-free sometimes. But my question is, when we can't make the guarantee that mutated code is error-free, like what's your technique to introduce it back into the population? Say if we generate a C code that doesn't compile, or if we divide by zero.
Right. So dividing by zero is a good. So there's a question of like, how do we kind of maintain error freeness? I think was sort of and I think the C code that doesn't compile, that's hopefully you've built mutation and recombination operators that would prevent that. But the divide by zero, that's something that absolutely could happen because it's the syntax is fine. You can, I mean, so in a real GA, you usually also have elites that we haven't focused a lot on, but commercially available genetic algorithms maintain elites. And so these kind of give you some institutional memory so that if you didn't have those errors, then you don't throw away perfectly good code just to replace it with mutated code. So usually you have a diverse enough population that if you found good solutions that don't have those errors, if they're performing well, they stay in the population. And so if you introduce something that has like a divide by zero, hopefully that has such a fitness cost that it'll get wiped away in the next generations. But I mean, these are all difficult problems. You might be able to actually penalize if you happen to see, there could be certain coding structures that you try to prevent from mutating. So you can actually say that like the allele that would give you divide by zero, there might be ways to prevent that ahead of time. So, there's sort of bespoke solutions to each particular application that I think you can work on there.
And it's these things called hurdles, or basically you'll run the program for like a really hard short example. And say it doesn't compile or fails like the divide by zero or something like that. Then it gets rejected and actually mutated until it passes this small test.
Right. So there's so beyond kind of the scope of this discussion, this sort of the evolutionary approach to designing programs and designing and sort of other things, there are ways to sort of add selective pressure in other interesting sort of ways. Like I've sort of said that every generation you evaluate fitness once, reshape your population, and then go back into it. And so what was brought up is that there are additional ways you can do it. You can say, well, I'm going to give them intermediate challenges. I'm going to allow things to evolve for longer before I, evaluate their fitness and so on and so forth. There are definitely ways that people have experimented with that help to improve the outcomes for these things. They are heuristic as to, which ones are going to work. I can't say that this is always going to work better than this one, but there are definitely problems that people have out there. And so I encourage you to look into those sorts of things, is that if you ever do want to use an evolutionary approach to do something non-traditional, then start with the standard kind of GA architecture, but then feel free to kind of say, well, what the GA is missing this particular solution, these sort of adjacent possibles are not being realized by my GA because it just doesn't give it enough time. And then so feel free to kind of adjust the GA to do that as you do your own work. But the kind of salient features, I think, will still be there, but you'll just kind of be playing with what you do with the population. So, all right, so that's, I think, all I kind of wanted to say about GenProg. There are people that, the applications for GenProg, some of them, not only is it writing programs, people are also doing with circuit design. So FPGAs, for example, field programmable gate arrays, you can have them be designed evolutionarily. Also decision trees. So medical decision trees have also been evolved with GAs. And so somebody comes in with a certain set of symptoms, how do we diagnose them? Well, a medical decision tree really is a graph structure that can be evolved on, just like using these sorts of methods. And so you can break it up into an abstract syntax tree, and then now you've got a decision tree that you can try different decision trees for as classifiers for different conditions based on people who present with certain symptoms. So that's another thing that people have used these things for. So a lot of applications, but again, it's just a standard GA, just with an interesting encoding that allows you to take graphs and evolve over graphs instead of evolving over numbers. All right. So that's all that I wanted to say about AIS and evolutionary programming, evolutionary computation for programming. in the last few minutes here, I'd like to introduce our next section on multi-objective. So before I do that, are there any other lingering questions or thoughts about using evolutionary approaches to build programs? It's like online's okay. Okay. All right, so something that is going to start out very different. Multi-criteria decision-making and Pareto optimality. All right, so at this point, we're pivoting away from thinking about problems that have a single stakeholder or a single optimization objective and trying to think about how do we find rich sets of solutions that somehow respect the fact that we may not know which optimization objective is best, or we have a whole set of optimization objectives and they're all important to us, but we kind of need to sort of have them all exert tension simultaneously on the solutions that we're searching over. And so what do I mean by that? Well, this area of multi-criteria decision-making, a subset of it is game theory. And so consider multiple players in a game that each have a particular utility function that is parameterized by, so this is utility function 1, it's parameterized by the strategy of player 1, as well as the strategies of all the other players. How many players do I have here? In lowercase n. And so player 2 has got their own utility function parameterized by player 1 strategy, player 2 strategy, and so on, all the way up to player n. All right, and so just to be clear here, down the diagonal are the strategies of the player that is related to that utility function. So the utility function is the value returned to that player. So player 1 plays strategy X1, so they decide to put this action. So if they're playing a game, poker, whatever, or even if the game could be choosing a fuel-air mixture or something, they choose one particular strategy. So you can think of this as an allele in a genotype. It would be a perfectly fine way to view this. And they're going to get a particular return out, but their returns are determined not only by what they choose, but by what everyone else chooses as well. Each other player chooses some other aspect of this big decision vector, and they receive some payout that may be different than the payout for that first one. And that payout will depend not only on player 2's choice, but on all the other n-1 choices. So this basic structure of this is a competitive game. Has a solution. Well, there's many different solution concepts we can come up with. And one of the solution concepts that we come up with here is a Nash equilibrium. And so the Nash equilibrium, so one solution concept is the so-called Nash equilibrium. And the Nash equilibrium basically says that for every player, so for all players, okay, for all player I, then we have the condition that the utility function for player I, and I'll define what these next things mean here in just a second, xi star, x minus I star is greater than or equal to the utility function for that player, that same player I, for xi and x minus I star. And I'll say, and this here is for all I. So I guess I could say for all xi, for all I and for all xi. So this is for all xi. Okay, so what I'm saying here is this is a no regret condition. So what I'm saying here is that there is a solution, and so this Nash equilibrium, this is the x1 star, x2 star, all the way up to xn star. That's what we're defining. These stars define our Nash equilibrium. And the notation x minus I is star is going to equal xi star, or it's going to be xi minus I star is going to tell us that we have x1 star all the way up, and I'll leave a blank space, to xn star, and then this is the ith position. So this means everyone else is at the Nash. So this notation here is saying that if everyone else is playing their component of the Nash equilibrium, and they continue to play their component of the Nash equilibrium, if I shift away from my component of the Nash equilibrium, I will do worse. So if we're all at the Nash and everyone else stays the same, but I decide to take a unilateral change, so I decide to change my decision variable a little bit, I am guaranteed to do worse than I am by staying at the Nash. So that's what we've heard, a no regret condition. So I'm not saying that it's not possible for me to do better, but for me to do better, I would have to get you guys to all choose to do something else too. So as long as you aren't going to change, this is the best thing for me to do. And as long as I'm not going to change, that's the best thing for you to do. That's what the Nash equilibrium is. It's not the best for everybody, but without coordination among individuals, it's the best we can do individually to defend ourselves. All right, does that make sense? No unilateral regret, where unilateral is the key condition there. So this is a not trivial to solve for. It's not trivial that this solution even exists all the time if I have a bunch of these decision variables. And so these could be the different stakeholders care about different things in my decision problem. So this could be the cost of water in Phoenix. This could be the cost of water in Las Vegas, and so on and so forth. And so there's different values for different stakeholders that are being reflected here. And I'm trying to somehow say, what solution are we all going to reach if there's no coordination amongst us? That's Nash equilibrium. And so to solve for this, for continuous games, and by continuous games, I mean xi comes from an interval, a continuous interval, then a sufficient condition, well, a necessary condition for the no regret condition is that all the partial derivatives are equal to each other and are equal to 0. Is basically the partial derivative of the first function with respect to its decision variable is equal to the second with respect to its second decision variable is equal to The nth with respect to the nth variable is equal to 0. So basically, we have n, so to find the Nash, we have n gradient climbers converge where each is on a stationary point. And this is a bit of a weird condition to imagine, because what it's saying is that I feel my utility function and it tells me that this is uphill. So I'm going to walk uphill. The instant that I stand and move uphill, your utility function changes. So the world shifts under your feet. So what might have been uphill for you is now downhill because I've shifted, because I have control over your utility function. If you move, you're going to change my utility function. And so what was uphill for me after you move may now be downhill for me. So it's not a trivial problem to solve. But when we do reach our Nash equilibrium, if we get there, if it exists, then this will be the condition. So that I will finally be standing on my decision variable at a particular spot in my decision space where the gradient will be flat. I can't move upwards by going left or right. And then you will also be sitting on yours where the gradient is flat. And so we'll all be sitting at the top of our own little hills. If I move and you don't move, then that actually changes all of our hills simultaneously, but I am guaranteed to go downhill. I cannot move in such a way that will make me move uphill unless I can convince all of you to move in a way that's better for me, and I'm not going to be able to do that. Yeah.
And so based off like that example, then if you move a little bit, you'll do worse. But then if I'm not moving, I do way worse because I don't know, I have no control over what you do for my
Right.
like really screw over other people.
Right. You could, yes. If your intent, but then your utility would be the negative of their utility. So if you define your utility as a negative of another utility, then like you can get, I mean, that's the, but eventually, there are many types of these games that actually do have a Nash equilibrium, and this will be the condition of their Nash. So I bring this up because this is one way we can think about multi-criteria decision making, where we have a bunch of stakeholders that can change independently and affect the outcomes for every other stakeholder. And so then we have to say, well, where do things level out? There's another type of decision-making that is referred to as Pareto optimality. That is a much more sort of constructive solution concept that has to do with how we combine all these together. And Pareto optimality is going to be the focus of how do we find Pareto optimal solutions. And so I introduced this just as an introduction to multi-criteria decision-making, that there are multiple solution concepts. The one that you're probably most familiar with, that you've maybe heard about in popular media, is the Nash equilibrium. And the Nash equilibrium is a competitive equilibrium where individuals don't have control over any other individuals, so we can't imagine they're going to coordinate. And so we don't focus so much on the trade-offs among individuals. Each individuals just try to do their own. So next time, we're going to introduce a different solution concept. Referred to as Pareto optimality, which is focused on solutions where the only way I can do better is for you to do worse. And that doesn't sound that different from competitive, but it is very different because I actually don't know in the Nash case, it really could be that we all could do better if we all took a step to the left. But there's just no way I can get you to take a step to the left, so we're all stuck here doing worse. In Pareto optimality, it's going to be a solution concept where if you're at the Pareto optimal solution, if I do anything that makes me better, it definitely makes one of you worse. And that ends up being a very useful solution concept for decision makers because it characterizes trade-offs. And that's what we want to do is build genetic algorithms that find trade-off manifolds. And then we can give those to our decision makers. So that's where we're going. That's all I've got for you today. So I'll see you on Tuesday. Don't forget Muddy's Point on Sunday, and that mini project, I guess, is on Sunday. And then there's that concept check that's on Sunday. Remember, your bottom 3 concept checks are dropped in case you don't want to do this one. This mini project is not dropped, though. And I think that's all I got for you. So we'll see you next week.
When you ask in the mini project, explain your choices, you just mean like the probabilities and how like basically I structured my algorithm, or what are the choices?
You mean like the very top where I say,
Yeah,
like, yeah, pretty, but as I sort of say, you can choose any hyperparameters, any that you like. Just sort of, I just want you to tell me what you chose.
Okay.
You don't have to like justify it any great deal or like say like, well, I chose 0.5 instead of 0.6. But I just want to know, like, you know, how did you structure your GA?
And like my termination condition with that was how I got rid of the solutions that were outside the range.
Right. So everything I would need if I wanted to reproduce your solution.
For the first question, I got.
Oh, let me just end the recording here. And then I can. So there was a question online. And I think I can answer these questions next time. I don't know who's still available here online. So I will feel free to ask these questions again. I think some of them will get answered automatically. And so I'll next week when we restart on Tuesday.